Water distribution systems worldwide face great challenges as aging infrastructures require significant investments in rehabilitation, replacement, and expansion. Recently, the United States Environmental Protection Agency has called for $335 billion in investments for water distribution systems. For an investment of this scale, the environmental impacts must be known. Drinking water systems are thought to be major consumers of energy. For example, water transmission in California is estimated to use 3% of the state's total electricity, but a lot more information is needed to identify the best options on all levels of decision making. In particular, utility managers must be equipped with the best information possible to reduce both environmental burdens and economic costs. This research identifies options available to water utilities for reducing greenhouse gas emissions through investments in their infrastructure. We have used life cycle assessment to estimate greenhouse gas savings potentials. This study has expanded on previous drinking water systems assessments by including infrastructure aspects previously excluded, such as water tanks and booster pump stations, and by introducing new perspectives. In this article, we have focused on reducing water leaks and selecting pipe materials with emission savings in mind. Leaks are problematic worldwide, and loss levels over 30% are common in the United States and elsewhere. The American Society of Civil Engineers estimates that 71 billion gallons of water are lost daily in the nation due to leaks. We have developed a decision support tool to help utilities analyze the environmental effectiveness of leak management decisions. To illustrate the possibilities, we have created a greenhouse gas footprint of a case study utility in the western United States. Pumping energy is found to contribute 81% of emissions to the total footprint, which is compounded by substantial leaks as the case utility loses 40% of water destined for customers. We have found that in order to minimize emissions from leaks, pipe replacement should occur no more than every 20 years. The case utility replaces pipe every 300 years, and the U.S. average is thought to be around 200 years. Including life cycle modeling and evaluating pipe materials, we have found that polyvinyl chloride and cement-lined ductile iron are the Pareto efficient options when economic costs and greenhouse gas emissions are considered. Reducing leaks can have economical advantages too, and these are taken into account when assessing different scenarios through carbon abatement costs. It was found that leak reduction could be a more cost-effective greenhouse gas reduction option than renewable energy technologies. These methods used in assessing the case utility were applied to the drought-stricken states of Texas and California, and it was found that reducing leaks by 5% in California alone would exceed the state's estimate for greenhouse gas reduction through energy efficiency improvement in all of water infrastructure. For utility managers and policymakers seeking greenhouse gas solutions, leak reduction could represent a low-hanging fruit for cost-effective emission abatement.